Okay, 11.3.5, how much will I need? Exponential functions and linear inequalities. In this final problem-solving challenge, you will use your knowledge of exponential growth and decay, as well as linear inequalities, to solve some problems in planning a big parade. So before we begin, exponential functions generally follow this format. Here, y is equal to a times b to the x, and a is our starting value, b is the percent increase or decrease, and if so, increase or decrease, and of course x is generally, in this case, just time, or how many intervals. Hours, days, minutes, whatever. And this percent increase or decrease, if it's a negative 5% or a decrease of 5%, we would end up using 0.95 as our percent decrease, because each time we're going to multiply this times something less than 1. If it is a positive, if it's an increase, positive 5%, we would end up using 1.05. And that's just kind of the way to think about that. And linear inequalities, that's y equals that mx plus b. And I'm using equals here just because of, I'll show you in a second, this is our rate of change, is represented by m, and b is our starting value here. And inequalities, we need to remember that we have these sort of things. We have less than or equal to, greater than or equal to, less than or greater than. This one we would shade below. This one would be above. The next one would be above. Reorganize this here. If you see this, you shade below, and it's a solid line. Because the y value has to be underneath. Generally speaking, when we would see this, we would then shade above and solid. And it would be a solid line. If you saw this, it would be dotted and below. And in general speaking, if we saw this one, which is greater than, it would be above and dotted. So that's just some general shading techniques that we've used in class. Of course, it depends upon where the x is, or the y, rather. So you would have your function over here. So the function value would have to be less than whatever is over here, and that's why it's below. Here it would be above. This one would be below and dotted. And that's when you graph the equation. So today we're going to be using growth and decay. So this one here is growth, where we have a decimal number larger than 1, and this one here is decay. So using all this, we're going to plan a big parade. So the Cinco de Mayo parade, the town of El Fierro León, Texas, puts on a massive Cinco de Mayo celebration every year. Cinco de Mayo is a Mexican heritage celebration commemorating the Mexican defeat of French invaders in 1862. People come thousands of miles to be a part of this event. The celebration includes a spectacular parade at 4 p.m. on the 5th of May. Although it is not well known as the Rose Parade in California or the Macy's Parade in New York City, the El Fierro León Cinco de Mayo parade and celebration has a much larger attendance. Almost makes me want to go see it. So we've got to control traffic. We have to plan for hotels, tacos, feeding the people, and then getting people to and from the parking lots. So this is what our task is. So traffic control. So of course, traffic will increase on the highways just before the parade. The Texas Highway Patrol uses the expected rate of traffic to decide how many officers to put on duty, all part of city and police planning. Traffic is often measured in 5-minute intervals, so when an officer says 50 vehicles pass by a place, that officer means that 50 vehicles pass in a period of 5 minutes. Okay. So on a typical morning, 133 vehicles pass the El Fierro Leon Bridge. Well, that's pretty much 133 vehicles on a regular morning, non-parade day, 133 vehicles every 5 minutes, which is kind of a lot. That is a lot. So, but starting at 8 a.m. on parade day, the traffic increases by 19% each hour. So we have an increase of 19% each hour. So that's our rate of increase then is going to be 1.19, because if the initial thing is 100%, we increase it by 19, that's 0.19. So this is going to be our B. So how many cars pass the bridge as the parade starts at 4 p.m.? So we've already got some facts for this one. That's not too difficult. So let's go here. So on a typical morning, 133 pass. So this is our starting value that we're baseline. That's going to be our start at 0 hour. When time is 0, that's our start. Then we have our increase of 19% each hour, which was 1.19. So anytime before 8 a.m., we have this. We have 133 vehicles passing every 5 minutes. But starting at 8, it increases by 19% each hour up until the parade starts at 4 p.m. So this is our number of hours until 4 p.m. So we're going to start at 0, and the first hour will be 8. So if we go with 133 being 0, then at 8 a.m., we have it increasing by 19% each hour. So from 8 to 4, so that's 8. Let's see, to 4, that would be, let's see, 8 a.m., that's 1600. 4 p.m. is 1600. Is 1600 hours military time. 8 a.m. is 0800. So that's a total of 8 hours. So there we go. So now we know what our time is, how long it is. So our equation, if we go with this form of y is equal to a times b to the x, we now have all our pieces. This is going to be the total number of cars. So this is our cars. Here is our y, total cars. So we have y is equal to a is our starting value, which is 133. And we're going to be multiplying that times whatever b was. B is our rate of increase, which is 1.19. And this, our x value here, is 8 hours. So that's what we got. So x is our hours. This is our increase rate. And this a right here is our starting value. So all we have to do now is put that into a calculator and crush it. And when we do that, we're going to get y, which is the number of cars, is going to equal 133 times 1.19 to the power of 8. And after doing some calculator crunching, we get 534.84. We get 534.8442844. So we'll stop it there. And since we're going to plan for the number of cars, we're going to be rounding up because we want to be on the safe side. So we are going to have approximately. So then at 4 p.m., we're going to get approximately 535 cars every 5 minutes. And so that just basically means that that's what we have passing that point. So 535 cars. So our next question that we got to answer is this one here, which is the Texas Highway Patrol uses the model N equals 1.005 to the V to plan for the number of officers on duty. V is the number of vehicles in 5 minutes, and N is the number of officers that are needed. So we're trying to figure out the number of officers that we need. So this is actually, so N is the number of officers that we need. And V is the number of vehicles. And we know that V from the previous problem is 535 because we've already calculated that here. So this is actually end up being our V, or vehicles. So V is 535, and this is going to end up being actually f of V is N, just because the function N is a function in terms of V. So f of V is what is actually going to be N. So what we have here is they use this, and so now we just got to put that in here. So we have the multiplier here, which is 1.005, which is 0.5%. Anyway, just for a little number thing here, this is equal to a 0.5%, which is an increase of 0.5%. So that's what that means. And so what we have is we just got to put it in there. So let's just start plugging and chugging, and let's do this. So 4 p.m. And so how many officers should they have on duty? Officers on duty, this is what the equation is. So we get f of V is going to be equal, the function in terms of V is just 1.005. To the 535. So in planning this out, we have 535 vehicles. This is our increase that they want to do for every number of vehicles. So we end up with f of V, in this case, is going to be equal to 14.415. So we get 14.42. So we'll say between 14 and 15 officers. So they're going to need 14 to 15 officers on duty. And so the percent increase is this part here. So this little tab here, what is the percent increase? That is this. It's an increase of 1/2 of 1%. 0.5%, otherwise known as 0.005. That is our increase over what's normally done. It's going to be increasing. So that's how many officers they should have on duty. They use this function to do that. They just got some math going on, the police officers. So that's at 4 p.m. on duty. Now, by 4 p.m. though, yes, that's by this time. But as is with all parades, we go to the next question. By 4 p.m., there's going to probably be some out-of-towners that are going to be partying too hard. So these are non-locals. So everybody invades the town. So for celebrations like this, the Highway Patrol adjusts the model by what it calls the K factor. If the model f of v is f of v, the model called f of v, which is what we've been using, which is right here, f of v, and so what we end up with is this K factor. And so if we have f of v, which one do we recommend? Are we going to recommend adding K to this, multiplying it, multiplying the whole function by it, multiplying K by it, or just adding K to the function, the rate of the f of v inside? So that'd be n plus K in essence. So let's see if we can look at that. If we know that K is going to be 3, they just use K equaling 3. And we know that regular f of v is, we're going to, let's call it 15. Let's call it 15. Just so we have a number. So here we are just adding K to f of v, and K is going to equal 3. So if we look at which one of these would make the most sense to do. So if we just add K to it, so f of v, the function of v plus K, which we'll just call this one the blue one. So we got f of v plus K is going to be 15 plus 13, or 15 plus 3, which is 18, which is not that big of a difference from this. Then we have f of K times v. And so we're multiplying. If f of v, though, f of v is also this. So if we take K times that, so we're going to go 3v here. We have the f of v, keep in mind that f of v was also this. So if we're going to multiply f of v times this, we would get something different. And what we end up with is f of kv is going to give us, f of v is going to give us a huge number because our value of v, this is v. So if we multiply, that's our v value right here, is 535. So that would be the function of 535 plus times k. So that's 535 times 3, which is going to give us 1605. So then we take 1.005 times 1605, which gives us a massive value of 2,995 officers. And that's a lot. Now, if we have K times F of V, if you take K times F of V, and it's a little bit different here, K times V, V times K, that's this one here. So we do this one's green. This one here we did in blue. We'll do this one here in red. So if we take K, which is 3, times F of V ended up having a value of 15. So we have 3 times 15, which would just be 45. And then finally, V plus K. So the function of value V plus K. Which is going to be 535 plus 3, which is 538 times 1.005, which is our new function value. And so we put that in the calculator, and we go 1.005 to the power of 538. And that's basically 14.6, which is the same number. We get 14.6 for that one. Which is the same. So what we're looking at here is this 18 here is really close to 15. That's almost 15. Not much of an increase considering it's at 4 p.m. with all these non-locals. This is just too high. Nobody has 3,000 officers for a little town. This is too high. This is practically the same. So probably what would make sense is by having, if you go from 14 or 15 officers and you triple it by 4 o'clock for the K factor, this is probably more reasonable. This one is a little bit more reasonable. Sorry, this one makes more sense. So we're going to use 3 times F of V. Because this is just, that's an insane number of people for the number of cars. So that's what we're going to use. So we'll use this one. So no, no, and no. Okay. Hotel rooms. So hotel rooms. If the hotel rooms book up far in advance of the parade, the number of vacant hotel rooms decreases exponentially. Okay, so we just figured something out here. Okay, unfortunately, the data was lost. So it's known that there are 15,500 hotel rooms in El Frio Leon and the towns surrounding it. So that is the total number of rooms. 3 months after the hotels start taking reservations, there's only 992 rooms left. How many months were there less than 5 rooms left? So by what percent did the number of vacant rooms decrease each month? Okay, so what we have here is we know that it's exponential. Number of vacant hotel rooms decreases exponentially, which means we need to have something that looks like y is equal to a times b to the power of x. And so we know that there are 15,500 hotel rooms total. So when time is 0, we got 15,500 at the start. We have 15,500. And after 3 months, that has gone down to 992. So we know then that right here, this 3, that is our time, or how much time went by. So that's going to end up being our x value. And our starting value is right here at 15,500. So here's what we have. So we got our starting value. We know that this is where it starts from. And then 3 months, and then we end up with 992 that are left over. So we can build this. So we know that after 3 months, there's 992 when we started at 15,500. So now we got this. So we know we have 992 are left over after we started with 15,500 times some multiplier, which is this, we don't know what that is, the percent decrease, so we'll just call that B, and it was 3 months. So all we got to do is figure out what this B is simply by, we could divide and do all sorts of nice things, and that's what we're going to do. So let's just see what we can get here. And then, so we can start by dividing out this. So we end up with 992 divided by 15,500 is going to equal B to the power of 3. And 992 divided by 1,500, 992 divided by 15500 is 0.064, which is equal to B to the power of 3. And then all we have to do is undo this cube, or to the power of 3. So that just means we just got to take the opposite of that to both sides. So we are going to take the cubed root of 0.064, and that's going to equal our percent decrease or increase, probably decrease, because the hotel rooms are going to go down. So that ends up being 0.8. But we can verify that by just simply going the cubed root of 0.064 into our calculator, and we get, it's 0.4. There we go. So this is 0.4, because 4 times 4 times 4 is 64. So this ends up being 0.4 is equal to B. And so what we end up with here, since that B is 0.4, that is actually a 40% decrease is what that means. Because 0.4 is 0.40. No, hold on. That is a 60% decrease. Because if 100% or 1.00 is 100%, and then we have a decrease here of 60%, which is 0.60, this is going to be 40%, which is 40%. And that's what our B is. So what we actually, B here is 0.4, or 0.40 is our decrease amount, which is a decrease of 60%. So it goes down by 60% each month as it gets closer. So now what we have is we have our equation and some work here. So now we've got our equation, which is y is equal to our starting value of 15500. That's our start, times our b, which is 0.4. All of that, we're going to try to figure out how much time goes by, which we'll just call time. And we have to figure out until this is 5 rooms, I think. Only 5, less than 5 rooms. Okay, so less than 5 rooms. So if this value here has to be less than 5, so this is going to be, we can figure out when this is 5 and just go to less than that. So anyway, so the number of rooms, so we can work this out here. We want to figure this out for when y, how long it is less than 5. So when does this become 5 is really the big key. So how long before it's 5? So that's kind of what we're working with. So now we just kind of can work with this thing. You can build a table with it if you want. I'm going to give it a shot with the equation. You're free to use the table. So here we go. And so first thing that we would do is divide 5 by this 15,500. So we just take that 5 and we're going to divide it by the 15,500. And that's going to equal 0.4 to some exponent. And to further problem solve this, we know that after 3 months, it goes to 992. So let's just try 4 months, if it's 4. So let's just see if we can start getting these values here. 5 divided by 15,500 is 0.000322. So let's just round this to 0.00032. And that's got to equal 0.4 to some exponent of t. And well, we know that after 3 months, okay, we have 992, which means obviously to get to 5 rooms, it's got to be more than that. So let's just try it at 4. So let's just try when t is equal to 4. If t is equal to 4, okay, and I suppose we probably didn't need all of this. We could just do this and see if we get 5. Yeah, let's just do this. We got 15. Let's try it when t is equal to 4. And then we're going to try it when t is equal to 5. And if we need to, when t is equal to 6. So all we're doing is we're plugging t in for that and seeing if we get a number that's less than 5. So here we go. So this is actually what we're going to be working with here. This is actually what we're going to solve. So we know at 3, we're at 992. So we're going to go with 4. So if we got 15,500 times 0.4 to the power of 4, we get 396. When t equals 4, this is 396. So we have 396 rooms when t is 4. So that's not going to quite work. So let's see what it is when t is 5. 15,500 times 0.4 to the power of 5 is 158.72. So that's a big drop off. So 158, so we'll just say 150, I would just call it 158, but we're not to 5 yet. Okay, so that goes down by that much. I'm going to try 10. Let's just see what happens when we have t is equal to 10. If t is 10, so we have 15500 times 0.4 to the power of 10, and we have 1.6. So now we have 1.6 rooms, which is basically less. So now we have 1.6 when t is 10 in here. And so let's just try another one. I'm going to go less than 10. I'm going to just say t is 9, because that's really, really close to 5. This is really far away. So I'm now going to say 9. So we got 15500 times 0.4 to the power of 9, and that's 4.06. 4.06. And based upon how much this is changing, I'm probably going to say this is fine. That's less than 5 when t is 9. So at 9 months, we have less than 5 rooms. So let's go back up here to our original problems. How many months? Well, we have 9 months. We have 9 months. And then what percent do the number of vacant rooms decrease? It's a decrease of 60%. So we have a decrease of 60%, which is 0.60, which means we have a multiplier, or we have a factor, this exponent, this multiplier b, which means b is our multiplier, is 0.4. So that's that problem. So now we got to talk about tacos. Because you got to feed the people and you got to give the people what they want. So there are 15 taco shacks along the parade route. People wait long lines to get their famed tacos because apparently the tacos are awesome. So looking back at the last 5 years, this is all the data we had. So this is it. Right here. Time of day, 8 a.m., noon, 10 a.m., noon, 8 a.m., etc. These are some trends of data. Apparently we got 2 8 a.m.s. We got 2 nooners, 2 noon data points, and we've got 1 at 10 a.m. Okay, so based upon what we've already learned about the celebration, what type of function should the food director use to model the number of tacos? Well, if we look back at what what did the police used? The police used let's see right here, we had increases by 19% each hour. This one was exponential. This was exponential growth. Okay, this one here, this is exponential as well. So for the traffic, we used exponential. For the hotels, it was exponential. So traffic is people coming into towns. Hotels are how many people are staying in town. So the traffic used exponential. The hotels were also exponential. So it almost makes sense that the food would also need to be exponential. If the people driving in is exponential, the people staying there is exponential. and we're probably going to have exponential food consumption. So what we have to do is kind of come up with some form or sort of equation for this. And so that's going to be a little bit difficult, but I'm going to use some average numbers for these 2 noons and the 8 a.m. and between them because we only have 2 data points. And here's an example of what I mean. If we were to take these and we put them on a graph, okay, at 8 a.m. we would have 2 spots like this. This is at 8 a.m. At 10 a.m., we have 1 spot, which is something like this. There's our 10 a.m. And then these are going up 2,000 and 2,000. So whatever these numbers are, we're going to end up with 2 up here. And so what I mean by since this is saying exponential, here comes the issue. Just look at this cheap diagram here, is that you could fit this with a linear line. A linear line of best fit could go like that, something like this. But that wouldn't be exponential because this is 10 a.m., this is noon, 12 p.m., and we still got to get all the way out to 7. And so, but the problem comes into play with this. So bear with me on this little explanation as to why it is that I'm doing this. And so these 2 points and these 2 points, we can come up with an average that's in the middle. But we don't want it to be, we know that we're going to have exponential people. And here's why. So if we take this thing all the way out here to, let's just say 7 p.m. So that's every 2 hours. This would be 2 o'clock, 4 o'clock, 8 o'clock. So this is 8 p.m. out here. Okay, and so then we got this, just as a quick sketch. So we got 8, we got 10, we got 12, and then we've got 2, 4, 6, and 8. So 7 p.m. is going to be somewhere in here. 7 p.m. will be right here. Now don't draw this because it's just an explanation as to why. So if we have an exponential curve, this is going to go something like this. And then by 7 o'clock, you're going to have this many missing. So this, if we go with linear, these will be unfed people. Unfed if we went with this line, which is why we kind of have to use the exponential curve. And it might actually go like this, and then maybe even creep up a little bit. You still end up with unfed people in here if you go with linear. And the last thing you want is a bunch of hungry, angry people that wanted their tacos and didn't get any. So we're going to use exponential. And I'm going to basically average these 2 numbers out. And we're going to see what kind of, so that's the concern. So if we are going to have, be careful of linear. Linear would give you unfed people. A lot of people. Unfed. So that's why we're kind of going to go with exponential. Because the other growths were exponential. So the other models that we used were exponential. So that would just be the big concern, is that if you chose to look at this and you could have gone linear with a line of best fit, but it's actually a curve of best fit. So this is a curve of best fit. So it's a curve, it's not a line. The line of best fit leaves a bunch of people hungry in there because there's this gap between the two lines. So now we're going to predict how many tacos we're going to have at the 7 p.m. hour using an exponential function. So if we have 8 a.m. to 8 a.m., so we take the average of 9:54 and 11:50. Let's just put this and make this a different color here. That'll be purple. So that just goes, that's the concern. Linear would leave a lot of people unfed. Exponential, because the other models were exponential, you get a curve of best fit. So now for 7 p.m., we know we've got to have Y is going to be the number of tacos sold. A is going to be, we could start at a.m. and see how many tacos we had. This will be our start value. Then we have B to some value, and then we have time here, which is the number of hours. So going from 8, if we sold these, because that's really all we have to go on. So that'll be our start time. Our start time is 8 a.m. So let's just see what we end up with all this. So if we take the average for the 8 a.m. group, 8 a.m. average is going to be 1150 plus 954 divided by 2, because we only have 2 data points. So we have 1150 plus 954, and we're going to divide that by 2. Plus 954, and divide that in half, and we get 1052. So 8 a.m. we have 1052 as our starting mark for averages. And then we have, because that's between the 2 dots. So the curve of best fit would be somewhere between those 2 points. That's the point in the middle. Then for noon, we have 10 a.m. is easy. We only have that one. So for noon, we got 22. So noon, the average is going to be 2257 plus 2091. And looking for the number that's in between that to give us this one. So we got 2257 plus 2091. Divide that by 2, and we get 2174. And so that's what we kind of got there. So we could use those 2 numbers, or we could round them up a little bit just to pretty much estimate this. But anyway, these are the numbers for what we have here, and then these are the numbers for here. And so now what we got, we got 10 a.m. is 1512. So we've got, let's see, 8 a.m. At 8 a.m. we got 1052. At 10 a.m. we've got 1512. And then at noon, which is 12 p.m., we have 2174. So what I'm going to do here is I'm going to take this, I'm going to make this into a nicer number. We don't really need that 1052. Let's just make that 1050. It's not that far away. We'll make 1512, we will make 1500. And then 2174, we'll just make that something nice, 2175. So that's the numbers that we're going to use for this, just to approximate and round to some near taco pieces. And we could actually round these even further. We could make this 1100, we could make this 1500, we could make this 22. So yeah, let's do that. So we're going to make this one 1100. It's right in the middle, but we'll go 1100. We will make this one 1500 just for rounding purposes, and this one will be 2200. And now we got some nicer numbers. Okay, so if we look at these now, and if we take to find the percent, we need to figure out what our B is equal to, or what is our percent. We know it's an increase, but just exactly what is it? Percent increase, which is our B. And we're going to get that by taking 10 a.m., which is this 1500, and we're going to divide it by 1100, which is our 8 a.m. value. And then we're going to take the 12 p.m. value, which is 2200, and we're going to divide that by what it was, and we'll get our percent increase, and that's 1500. So we just simply do some division on this. We do some division here, we'll get the percent increase total. Now we got to remember this is in 2-hour blocks, so this is for every 2 hours. Percent increase each 2 hours. So every 2 hours, this is what happens. And we're going to want to probably deal with that and cut it in half for every hour later. But let's just go with this. So we got 1500 divided by 1100, and that's 1.36. 1.36 is what we got, 364. Okay, and then if we take 2200 and we divide it by 1500, we get 1.46. 1.467. So if we want to get something in between that, we can go 1.364 plus 1.467, and that's 2.831, and we can divide that by 2. So we take these two, we add these, and then we can divide by 2, and we'll get something in the middle, which is 2.834, but then we want to divide that by 2, and that gives us 1.415 or 1.42. So this becomes 1.42. So it goes up by 42% every 2 hours. So every 2 hours it's 42%. We want every hour, so we just half that, which is going to be 21% increase each hour. Of tacos. So now we can build our equation, which is our tacos is going to equal. So then we have, this is every hour 21%. So the tacos are going to be our starting value, which is, we're going to go with 1100. 1100 is our start because that's what we started with. 8 a.m. We're selling this many, it's all we know. And then we have our 21%, which is going to end up being 1.21 is our B. So we got 1.21. And now we have to figure out is the number of hours between 8 and 7. Well, 8 to 8 is 12, so it'll be 11. Tacos by 7 p.m. And then, so if we go 8 to 7, 8 a.m. to 7 p.m., that's 11 hours. So 7 p.m., that's going to be 11 hours. So that's 11. And now we just got to crunch the numbers. So we have 1100 times 1.21 to the power of 11. And we're going to be selling roughly, according to this, for 11 hours. And we got a grand whopping total of tacos by 7 p.m. of, according to our numbers, 8,954. 8,954.3. So that would end up being 8,955 tacos, estimated tacos sold 7 p.m. hour. So that's a lot of tacos. So in 11 hours, it's going to go up each time. So we'll be selling a bunch of tacos according to this exponentially. So almost 9,000 tacos are being sold. And so we're increasing at 1,100. We estimated that. Now, if you went with 1052, this number could be different. But this is just what we did when we have our estimates here. So this number here we got from our averages for the time. And this is then our estimate to make the math a little simpler or look better. So that's what we got. 8,955 tacos being sold at the 7 p.m. hour. Boom, lots of tacos. Parking lot shuttles. Okay, so celebration organizers must decide how many buses and trams to lease to shuttle people from the parking lot to the parade route. They're working on a number of constraints. So whenever we talk about constraints, a lot of times that will bring up the subject of an inequality. Inequality. Space for writing. Inequalities, because something is usually going to be less than or greater than. So they're working on a number of constraints. One is there are at most 8 trams. So we know from this that the number of trams, let's make this black here. So constraint inequalities. So the number of trams has to be less than or equal to 8, and it has to be greater than or equal to 0. So this is an equation for the trams. Then there are 30 shuttle buses available. So we know that we can have for the buses, the shuttle buses, which is this we'll call S, has to be under 30, but you're going to have, well, at least you can have a 0. So that's what we have for this. So it takes 4 staff members to safely load and operate the tram, while it takes only 1 operator for a shuttle bus, and there are at most 50 staff members for this duty. Okay, so we can come up with an equation for that one. We'll do that one in green. So if we know that for the staff members here, for staffing, it takes 4 staff members for a tram. So we have 4 times the number of trams. 4 times the number of trams. And then it takes 1 person for a shuttle. So we have 1 person for a shuttle bus. And you add these two together, there are at most 50, which means this has to be less than or equal to the at most, which is 50. So this is going to be the equation for our staffing. And we move this S over, so then we got 4T is equal to a minus S plus 50. Then we divide everything, divide this 4 out, and we get T has to be less than or equal to a negative, this is a 1S, so it's 1 over 4 times the number of shuttle buses plus 50 over 4, which is 12.5. So now we have that equation. For staffing. So that's our staffing. And then now we get into the insurance. Yikes, because everything costs money. So insurance we're going to do over here in purple. So for our insurance equation, we have the basic insurance cost $10,000. So the flat rate, you're going to pay $10,000. Straight up. Each tram is an additional $1,000. So you're going to add in $1,000 for each tram that you use. but the shuttle bus is a discount. So that means we're going to take away so we add 1,000 for every bus, we take away 1,000, and we take away 1,000 for every shuttle bus, and we have a maximum budget of $15,000. So whatever we do here, that has to be less than or equal to $15,000. And so first thing I'm going to do is I'm going to divide everything out by 1,000, which means this then becomes 10. So take out 3 zeros, 3 zeros, 3 zeros, 3 zeros, divide by 1,000. So now we get 10 plus 1t, 10 plus a t minus an s has to be less than or equal to 15. And so we want this in terms of t, so we just move everything over here and subtract it, and then we end up with t, the number of trams, has to be less than, let's see, that's s plus 5. S plus 5. And that's our equation for the insurance that we can use, whatever it is. Now, if we take this and we take all of these equations that we have, and we've got 4 of them. This is the number of trams. This is the number of shuttle buses. And we follow that. So the trams have to be in here, and then the staffing, and then the insurance. If we were to graph these, wherever they all overlap, that's where we can do our business. It's the intersection of the solution of all 4 of these. So here we have a graph here. So our trams was 0 to 8, 0, and then our trams, and then 8 from the previous page. So that is number of trams has to be less than or equal to 8. So that's just pretty simple. That's just going to be here. We go to 8. It's all of those that are less than that. So everything that's underneath this. So t has to be between 0 and 8 for the trams. And then we have our shuttles, which was 0 to 30. Trams, shuttle buses. So here we have our shuttles. I call them a shuttle. They call them buses. Fine. Whatever. I'm going to call it S. There. I win. And so we then take that and we make it blue 30. So now we've got this puppy here, 0 to 30. So it's everything that's in there. And then our next equation for staffing was this madness, which was t is less than or equal to negative 1/4 s plus 12.5. So for staffing, we have t, the number of trams has to be, we said it was under, less than negative 1/4 s plus 12.5. So that means it starts at 12.5, which is 10, 11, 12.5, which is here, and it goes down 1 every 4. So if we can double this, we'll get it, let's see, down 1 over 4. Down 1, 1, 2, 3, 4. So it's going to be like that. Down 1 over 4. Right there. So that's the tram line. And when this is 0, this has to be 0. So S, times 4, 12.5 anyway. That's going to be something. It's going to be whatever. Down 1 over 4. Let's get a lot of data points here. And then we go, okay, let's take a line, make it green. Start at 12.5. Not what I wanted. Let's take a line, make it green. Right there. So that's that one. Okay, and so that is the green line. And so, okie dokie, let's just see something here. Let's get this closer. All right, that's kind of nice, here to here. So now we have anywhere that's underneath, it's under the red line, to the left of the blue, below the green works. So everywhere in here, these are not options because we don't have the people for it. So it's still just what's in here. Actually, inside this thing. Anyway, and then the last one for the money, híjole. The last one for the money, for insurance, T, it's under, whatever's underneath S plus 5. So that one was in purple. So we go to 5, and that's up 1 over 1, up 1 over 1, up 1 over 1. No, it's under. One moment. Sorry, getting lost in the sauce here. Okay, so this is going to be starting at 5, and it's going up 1 over 1, up 1 over 1. So that's what we got for that. So we will just start it at 5. And it's going up 1 over 1. There we go. So what we're looking for is we are looking for now anything that is underneath and between all those lines. So with the solution to this, so our possibility answers, our options, meet all constraints at the same time. So that's our solution at the same time. So it's everything that's underneath the purple, underneath the green, underneath the red, and to the left of the blue. So it's everything that's kind of in here. And so we want to kind of maximize that. So we could take this point here. We could take this point here, and we could also take this point here. Those are maximizing. So this is the maximum number that we can have for here, here, and here because we're on the edges of it. So those are pretty much our points. So we got 3 and 8. 3 shuttles. I'm sorry. Yeah, 3 shuttles, 8 trams. Here we have 8. We have 15, 16, 17, 18. Here we have 18 and 8. And here we have 30 and 5. That's what we got so far. So those are the points that will maximize everything because we're maxing out our staffing and our shuttles, and it's still to the left of this, but we're not maxing out our shuttles. We're maxing out our trams. So, and then here we're maxing out the insurance and our trams, and here we're maxing out the staffing and the shuttles. So these are our max points. So we got 3 points where we maximize everything. So anyway, those are 3 points. And so now, so that's where our solution is. Could be anywhere inside of this. anywhere in here. This is where our solutions are. It's anywhere in here. These are our solutions, and I'm articulating that because these are intersections, this maximizes, maximizes, and maximizes. So we maximize the shuttles. We're here. Or maximize, yeah, we maximize our shuttles. Shuttles. That's bugging me. Shuttles. So we maximize our shuttles. It's here. We maximize our staffing. We're here. That's the highest number of staff we can have. And here we're maximizing the trams, and our maximizing the trams, maximizing the trams, maximizing the shuttles. And that fits the staffing, everything. So that's why those are the maximums, because this is an 8. I'll show you here. This is an 8. Maximizing the shuttles, or maximizing the tram, max shuttle. So those are our maximum points. And so that's what we've got. Those are our options to max out. Anyway, but all our solutions could be anywhere in here. So, which combinations would allow the shuttle to shuttle or move the greatest number of people? A bus holds 30 and each tram holds 100. Well, we could max out here, and I'm going to say, let's just take these 3 points and see which one gives us the most number of people. So we got 3 for trams, shuttles and trams, shuttles and trams, shuttles and trams. So for our shuttles, for our trams, and our shuttles, this is the maximum number of shuttles with the maximum number of staffing with dollars. This is the best option for maxing out the shuttles. And then we got 2 options for here for maxing out the trams. And one is held by this constraint of the insurance, and this other one is held by this constraint of the staffing. And both of these are under the insurance. So we can't go above the red line or to the left of the blue. We can't go above the green or here. So we got to always stay in here. So we got 3 shuttles, 8 trams. So we got point number 1, which is 3, 8. The next one was 18 and 8. And the last one was 30 and 5. So these are our max points that I can look at. And the shuttles are times 30. The tram is times 100 for the number of people it can hold. And this is just the total number of people. It's not including staff. So let's just take this. Let's see, visitors, we'll call it. Total number of visitors. Total visitors. So we're going to take 3 times 30 because that's the blue, so the shuttles. So we got 3 times 30, 18 times 30, and then 30 times 30. And then for the trams, 8 times 100, 8 times 100, and then 5 times 100. Okay, so let's just look and see what we got here. So this is 800. So this is going to be 800 plus 240. This is going to be 800 plus 18 times 30, 540. Well, this one's obviously more than this. And then this one here is going to be 500 plus 900. Okay, so this one is still less, so I'm not even going to bother with this one because it's less than this. But let's just play the game. So this is going to be 1040. This is going to be 1340. And this is going to be 1400. So 5 plus 9, 5 plus 9. 14, 8 plus 5.4, 1340, yeah. Okay, so apparently according to this, the maximum here is right here based upon the graphed data. No crazy things going on. We just graph them and get them. So we can go with 30 shuttles, 30 of the shuttle buses, 30 shuttle bus, and 5 trams. And now we have planned our Cinco de Mayo festival. So don't forget the review and preview, and good luck, and see you online.